Hi, now we are on chapter 8 and we'll discuss acoustic porosity tools. So the main principle here is to use a transmitter which will change an electrical signal into a wave, and that wave will go through the borehole, through the formation, and when coming back at the receiver, that will give us information regarding porosity and other important factors that we'll see in a minute. The primary applications are porosity determination, lithology indicators, identifying gas-containing zone, to provide depth correlation for seismic sections, also to provide mechanical rock properties, etc. The logging conditions, since the signal that we're working with is sound, you can run an acoustic tool on fresh water, salt-based water, oil-based mud, but since sounds doesn't travel very well on air, so you cannot log it into an air well. So the physics of the measurement. Here is the main principle. We'll just generate the transmitter will generate a wave. So we're measuring the time it took from that wave to arrive from transmitter to the first receiver, and knowing the distance between this receiver and a second receiver, we'll calculate the velocity. In this image, you can see the transmitter here up here, and this particular tool has 4 receivers. So what you see here is the wave being detected first at the first receiver, then the second, third, and fourth, and so on. The velocity will be the spacing divided by the time difference. This is how a transmitter might look like, one type of transmitter. So when the transmitter, this is important to mention, when the transmitter is activated, as said, it generates a wave, but actually there are different types of waves that are generated. So actually there are 7, if I'm not wrong. So we have tool mode, mode wave, compressional wave, shear wave, leaky mode, normal mode, Stoney. So all those waves are generated there. And this is how a receiver might look like. This is the concept of offsets, which is the space between each receiver. So when you detect this signal, is everything, a bunch of all those previous mentioned signals, everything is in here. Compressional waves, shear wave, Stoney, flexural, all is there. On this graph, we can now start, depending on their velocity, we should find compressional waves on this area because they arrive first. So once the transmitter is activated, we start counting time. So compressional wave arrives. They arrive first, then shear, then Stoney. This is again a recap of all the type of waves created. Direct waves, they were called direct because they travel. The tool mode is the way that travels through the housing of the tool. The mud wave travels through the mud. We'll see the rest on the following example. This is an example why the housing of this particular tool is machined with those slots is to make the path longer, so to make a greater time separation between the arrival of compressional and shear, so you will be able to read it or identify it better. So this is just one way of doing that. Other type of tool they use like elastomers or other type of material to isolate that. And again, the same graph showing you the region of the mode wave. And here is an example of a compressional wave. They look like this. I mean, their displacement and their propagation goes in the same direction. This is the formula to calculate the velocity of the compressional wave. A few concepts to this is reflection when the wave touches and goes back. This is total refraction when the wave touches the interface between the Warhol fluid and the formation, and then it will go into the formation and you will never see it. And this is critical refraction. We're interested in this phenomenon. When the wave leaves the transmitter, goes through the Warhol fluid, and it goes on the down through the formation on a critically refracted way. The angle of this refraction will be determined by the Snell law. We will mention this later. This one. So this is what we call a critically refracted. And this is the critical incident angle. The shear wave, as you can see, the displacement goes in one direction and the propagation in a different direction. A comment on shear waves is that they do not travel through fluid because this number, G, which is the shear modulus of the medium, in this case G is 0, and this is why shear wave, they don't travel into fluid. They will not propagate through liquids. Another example. So a comment I just highlighted, the acoustic energy detected at a receiver and is used to compute the velocity is not actually a shear wave. So if shear wave do not travel through liquid, so how do we get that information? Actually what we're measuring is called a flexural wave. That this is the tricky part. We want to get shears, but since they don't travel through liquid, we then have another type called a wave called flexural wave that has the information that we want. So a flexural wave is a type of shear, to put it in that way. This is a Snell law, which explains how this relationship is done between the angle at which this wave is reflected. This is a key point. Acoustic tools, sometimes they use a monopole transmitter, sometimes a dipole transmitter, sometimes both. So check this out. Monopole acoustic transmitter, they fail to generate critically refracted shear wave informations where shear velocity is slower than that of the fluid pressure wave through the Warhol. So when that condition is present, your monopole cannot generate your critically refracted shear wave. Then you need a dipole, which a dipole transmitter will do that in all formations. And this is the key part as well. This flexural wave at low frequency travels at the same velocity as would a critically refracted shear wave. This is where the confusion sometimes is made. That you want the shear information, but they don't travel, so they don't exist. What happens at the end? You get flexurals, and flexural wave will give you the information needed. You have surface wave, leaky mode, and Stoney, which we'll not cover in very much detail. But you can read a little bit of that here. For calculating porosity, here are the values for delta T of the most common matrix like dolomite, limestone, and quartz, and the delta T for fluids like fresh water base, salt water base, or oil. An important things to cover here is the Warhol problem in acoustic tools. This is the ideal scenario. This is how things should go. The transmitter emits that wave, which will travel through the Warhol fluid, then being critically refracted through the formation and going back into the receiver. And the sum of these vectors will give you your delta T. But what happens here? If you have a phenomenon called tool tilt, where you can have a washout, and that poses a problem. It turns out that For tool teal, monopole transmitter will not be able to fix this problem, because in one area it will overestimate and in the other scenario will underestimate and washouts. Here you have washouts, then your vectors will be a mess. And the solution for that is to make a overall compensated dual transmitter. So if you put one transmitter on the top, one transmitter on the bottom, then that effect of tool tilt will be compensated like this. Can you see? There's another method for compensating that when you're using a long space sonic and the short space sonic. This is what we mean by long space and short space sonic, these distances. In this case, you have a monopole transmitter, and to put it in short, with a short space sonic, and if you have one monopole transmitter, you can compensate by washout, but you cannot compensate for tool tilt. And what you're going to need to solve that problem is, if you're using that, you'll need a centralizer, and that will fix the problem in that case. So that was a quick review, and thank you very much for watching.